Let's talk about the case when we are wanting to compare the means of two different populations, but those two populations are not independent of each other. Okay? In the previous two conversations we've had, we talked about comparing means, the differences in means, or looking at the differences in means of two populations, but we assumed that those two populations were entirely different from each other. The sample that we collected over here from population 1 didn't affect the sample collected over here from population 2. And in fact, the populations don't affect each other at all. But in some cases, we do have to analyze situations where these populations are not independent of each other. A lot of times this happens in before and after kinds of studies. Okay, we talked about this previously, before and after studies. So for example, a weight loss drug. We're wanting to determine if a weight loss drug works. So we have to look at the population before they took the weight loss drug, and then we give them the drug, and then we weigh them after they took the drug. Okay? It's the exact same people from the before as it is the after. Therefore, those two populations are not independent of each other. We're testing the weight before and after on the exact same person. Okay? So that means that those two populations are not independent of each other. We have to have an entirely different way to address these kind of situations. Okay? So how we do this is with something called matched samples or paired samples. And so let's say we have some observations from population 1, that's going to be the befores, okay? And let's say we have population 2, that's going to be the afters, okay? So here we've got Y11, okay? That's going to be that the before the population 1 first observation, this first person, okay? Let's even put a different column over here for I. So this is going to be the observation from each population. Okay, observation 1, we've got the observation from the first population, the observation from the second population, and those two correspond to the same person or the same thing or the same, whatever it is we're studying. This is a measurement from here. This is the measurement from the same place. Okay, so these two things are not independent of each other. Okay, we've got our second observation, and so on, for n different observations. So here's y1n, y2n, okay? And so what we do here is we calculate the difference, okay? What is the difference between these two values? Okay, so that's just y11 minus y21. This would be y12 minus y22, and so on down to y1n minus y2n. Okay? So these values are the differences, the before minus the after. Okay? I use before and after. It doesn't necessarily have to mean that, but that's just one easy way to think about this, before and after. Okay? So we calculate those differences. Then we find d bar, which is the average of the differences. The sum of the di's divided by n. And we calculate the standard deviation of the differences. That's how different is each difference, the difference from d bar squared summed across all I divided by n minus 1. Okay? So these are straightforward calculations. This is the mean, this is the standard deviation, both of those from a sample that we talked about several units ago. We're just applying it here to the differences, not to the actual observations. Okay? So now we've got the mean, we've got the standard deviation, and we can do inferential statistics on these differences. Okay? So we could have a confidence interval. What is a confidence interval for the average differences? Okay? That would be d bar plus and minus t for our particular degrees of freedom, alpha over 2, times s sub d over root n. Okay? Really straightforward from here, right? It's a very straightforward confidence interval, where degrees of freedom is n minus 1. We just have one n, okay? Because this population and this population both use the exact same number of observations, okay? And in fact, the observations lie in both populations. So that's our degrees of freedom. And our test statistic is a t-test statistic, okay? And that is, let's first talk about what we want to address here, okay? We want to know for example, is the mean difference, is the population mean difference equal to some value, or is it not equal to that value? Okay. Is this average difference 4, or is it not 4? Okay. Is this group bigger than this group on average by d naught or not? Okay. We could also do the same kind of other alternative, or the other hypotheses. We could look at greater than equal to in the null versus less than in the alternative, or less than or equal to in the null versus greater than in the alternative. Okay? Same kind of idea we've always been applying with respect to the 3 different kinds of hypotheses that we could address in inferential statistics and hypothesis testing. Okay? So now our test statistic. How different is the sample mean difference from the hypothesized population mean difference? Okay? How different is the sample evidence from the hypothesized value in standard deviation units? S sub d over root n. Okay? Very straightforward test statistic. Same kind of idea. Critical value approach, p-value approach, both work the exact same as they always have. If this is a lot different from this, then it's going to lie in one of the tails, and we'll end up rejecting the null hypothesis if these two are different enough from each other. If we have reason enough, if we have evidence enough to believe that, for example, the real mean is not equal to d naught, then this is going to be a lot different than d naught, and we'll reject the null. Okay? So inferential statistics for matched pairs, paired samples, matched samples, there's a lot of different interchangeable words that we use for this, where the 2 populations are not independent of each other.